Welcome. It has just gone 7 p.m. Wednesday, the 23rd of February, and you are watching episode 37 of Regional Wrap. Regional Wrap, providing insight to the issues affecting regional Australia and giving a voice to regional residents. My name is Bill Bates, and joining me on this episode is my guest, Dr. Mark Ho. Mark works at the Australian Nuclear Science and Technology Organisation, acronym is ANSTO, which operates Australia's only nuclear reactor at Lucas Heights, some 40 kilometres southwest of Sydney. He holds a PhD in computational fluid dynamics from the University of New South Wales and supervises 3 doctoral students on reactor-related research. Apart from running multi-physics simulations in support of the reactor, he keeps a watching brief on nuclear power developments. Mark is the Vice President of the Australian Nuclear Association, an independent scientific organisation representing the members of the profession and enthusiasts engaging in the government, industry and the community on all things nuclear. Welcome, Mark.
Thanks for having me.
If we could just start off with a bit of your background, your childhood education, the mischief you got up to maybe, and then what directed you into science and in particular the nuclear field.
Oh, okay. Well, yeah, so I guess I have to reach back in the history and my memory into what I've been doing. Well, I grew up in suburban Australia. In the Shire. I don't know if you guys are familiar with the concept of the Shire in Sydney. It's this region.
Isn't that somewhere on the beaches of
Cronulla
Sydney?
And Sylvania Waters? It's a beautiful place to grow up in. Awesome people, super friendly. I went to a little Catholic school, primary school down there, and then I went to a high school like closer to the city, in Sydney High, and then eventually I did just a straight mechanical engineering degree. At UTS first, and then the UTS program had an internship component, and that I thought was really great experience, because obviously you get book smart, but you really want to get hands-on and practical, right? And initially I was like working a little bit further south down in Bomaderry, like kind of past Wollongong, and there's a big starch factory there, and I started off as an intern in an engineering design firm called Miko Engineering. And then I got really kind of familiar with CADing, doing design work. And then the second internship I did was over at ANSTO. So, you know, they liked the fact that I got some kind of like design skills. And I worked at a place called the water tunnel facility, which basically is kind of like think of it as a wind tunnel, but with water. And they do tests with, say, you know, reactor components and do things such as measuring pressure drops across, say, a mock fuel assembly and things like that. And all that work goes to inform that, you know, we can operate the then reactor HIFAR safely and reliably. So as an intern, I did well. You know, I impressed some of the bosses, and they said, hey, you know, why don't you just do a master's with us, Masters of Research, because at that point in time, they were thinking about replacing this kind of 49-year-old reactor with something that's slick and new and reliable, which is now the OPAL Research Reactor, which stands for Open Pool Australian Light Water Reactor. And of course, you know, I said, great, you know, I really love the work and it's really exciting. And so this is how I kind of got dragged or, you know, sucked into the profession, is because it was such an interesting and exciting kind of a line of work. And it's really about the high-tech nature of nuclear science technology that really drew me into the profession. And then so afterwards, I finished my Masters of Research. I was looking at the stability of the new reactor fuel assemblies under flow conditions. And then they said, look, just get a job with us. So that's how I joined ANSTO. And it was actually only after I joined ANSTO that they then asked me to do a PhD part-time to go along with that. And in that regard, I worked on writing basically a big chunk of computer code to track the interface of bubbly flows, because when we're talking about reactor safety, we're really interested in the dynamics and how boiling occurs and the way that the bubbles form and detach and separate and recombine. And so what I did in my computer code was to model that in high detail so that we can pretty much like replicate, you know, what's going on in reality. So it's, again, more high-tech stuff, more, yeah, it was a lot of work, but it was fun and it was exciting. And now, like 20 years later, I'm still here and, yeah, doing well.
Well, I suppose one of the difference, well, just before the show, we're talking about Big Bang, and that's sort of focusing people on science, although it's a comedy. You've actually had a real job before you sort of got to this stage, whereas a lot of people go through university and come out the other end and stay in pure research in that. So I think do you think having that hands-on and sort of other work skills put you in good stead for the job you're currently doing?
Yeah, definitely, definitely. I always really like engineers who, you know, can kind of think on their feet and have practical experience. But at the same time, you know, we have to understand that ANSTO has a really, really broad kind of community of scientists and engineers. And this is really interesting as well, because like you would think that engineers are kind of like the practical type, right? We only got like a limited budget. We have to like satisfy this design brief. How are we going to do it? We're going to get a little bit creative and draw up all our skills to do it. With, you know, physicists and scientists, they're much more exact, you know, so like they will be like more skeptical. They might say, are you sure we can do this? You know, they'll be crossed all our T's and dotted our I's. So the thinking and the philosophy is a bit different. And I guess, you know, where I work in nuclear analysis section, where we have a combination of physicists and engineers, there's always this kind of like somewhat tension or professional kind of differences or, you know, critique of each other's work. And I think that's a skill, you know, that's actually a plus.
I was just smiling there in regards to thinking of Big Bang and poor old Howard, sort of not a doctor. And he's just an engineer, but you don't get a nuclear reactor built without engineers. So, and a lot of other things don't get done without engineering. So, you know, everyone just has to, it's a multi skilled workforce that's needed to get things to fruition. So
yeah, definitely.
If we just start off with the nuclear industry in Australia, I mean, I think for the world, the introduction to nuclear energy was Big Bang, you know, atomic bomb. I mean, that was that. Before that, I mean, you had people mucking around with uranium and X-rays and things like that.
Sure.
But the real nuclear age started with the nuclear weapons. And so I suppose that's one part of the fear that came on. And then, of course, we know everything about the 60s and the peace movement and the anti-nuclear movement. But Australia, although it's got a current ban on nuclear industry in general, but that act didn't come until 1998. So it's not, that ban hasn't been there as long as a lot of people would think it was there. And we've also had the history of allowing the motherland to come over here and blow up bombs on our mainland and that. So
yeah, so
that's probably the worst introduction to nuclear energy or nuclear industry you could have.
Yeah, I mean, in some ways, yes. But I mean, I think it's somewhat difficult to communicate with, especially the younger generation, just how real the Cold War was and how important it was to, you know, this idea of deterrence and everything. I mean, everything I'm saying is of course my own opinion. You know, I'm not here representing ANSTO tonight or even the whole of the Australian Nuclear Association. You know, I'm just giving my kind of best informed viewpoint. And yeah, sure, you know, from a kind of optics perspective, people might associate, actually erroneously, the connection between nuclear weapons and nuclear power, but actually they're very, very separate things. And there are a lot of countries which have nuclear power without a weapons program, for instance. You know, say South Korea, for instance, they've got lots of nuclear power, and Japan as well. But you know, that it was a really, really kind of heady age, like the dawn of the atomic age, right? We're talking about the 50s, like the atomic science and atomic power was something that the population, you know, in the US was extremely interested in. You know, they wanted they wanted to have reactors back then. And it's almost as if the enthusiasm for nuclear science back then is kind of like somewhat almost similar to the enthusiasm for renewables currently. It's very, very emotionally driven. Obviously, you know, like from the learnings, etc., we understand that, you know, nuclear as a science and technology needed to be well understood and carefully done. And so now we're in a situation where there is a little bit of a nuclear renaissance. That's actually a little bit underplayed. I would say there is a definite nuclear renaissance around the world, looking at building more reactors, just because reactors are not emitting any pollution. It just emits water vapor. It doesn't emit any CO2, and that's a big deal. And to be able to deliver that at will, dispatchably, is something that you could think of as kind of like a coal-fired power plant, but without the kind of CO2 or the pollutants going up the stack, right?
I think maybe now with the introduction or the proposal to buy nuclear submarines after the failed French purchase or contract that sort of fell in the water, now we have bipartisan acceptance or approval of that purchase. So we've got the Labor Party and the Liberals. So you've got the two major players, both on side in regards to purchasing nuclear submarines. Do you think that is going to be or help as a catalyst to get over this barrier that we've had there since 1998 with the ban on nuclear industries?
Yeah, it's a really great question. I think that first of all, you know, we have to be clear, especially with the way the announcement of the AUKUS agreement was worded. It was very clear that both from, you know, the LNP and federal ALP, they both said that this has nothing to do with any kind of removal of the ban on nuclear power. They said that outright. But however, you know, if you look around the world, nearly all countries which have, you know, nuclear-powered submarines also have a civilian nuclear power program. And it makes sense in some ways because, you know, a lot of submariners, once they've been trained to such a high degree on how to safely control nuclear power as a means of propulsion, you know, they're basically very, very well trained to also operate civilian nuclear power reactors, as we are seeing, you know, in the US, for instance. And so, you know, this question of whether having a nuclear propulsion program for submarines will help, I think it definitely will help, just because the mass of people that would be trained up and knowledgeable about nuclear reactors and nuclear science technology would rise. And then I think also, once people kind of can see that these submarines will be operating safely and effectively, then they're also more at ease with the idea of having nuclear power plants on land as well. But of course, this stuff takes time, you know, it's not just overnight.
Yeah, although neither party is sort of saying that they're going to take away the ban on that, the whole point is the public acceptance will probably grow, and so there won't be any losing votes if they do pull the ban down, because the public are more likely to embrace it as time, and especially now as we seem to be entering a new Cold War. I mean, we make no mistake about it, the Russians are at the Ukrainian doorstep, and China's in the South China Sea showing a bit of muscle. So we're going, that sort of, after the war came down and that friendship and all those things developed, they've definitely faded away. We now have a situation where we have to be more defensive in general. So
yeah, self-reliant.
Yeah. So I think the people of Australia will be more accepting. And like so, I think COVID has shown, or hopefully has shown our government and the opposition our weaknesses in our supply line and our resilience and our self-determination in regards to industry. So hopefully that becomes a bit of a focus as we go to the next election. At least talk about our supply chain and our need for more resilience and self-reliance. But we can only hope.
Yeah, I think you're on the, you got the finger on the pulse there, because definitely, the signal from the current government as well as the opposition is that there is a review on increasing our ability to maintain our own supply chains and to increase the level of, science, technology, and engineering and production and manufacturing in Australia as a sovereign capability, right? It's about sovereign capability development. It's about, our own kind of growth in our own infrastructure and ability to manufacture. And obviously tied into that is to be able to deliver low-cost energy to support manufacturing as well, possibly in a carbon constraint kind of environment. But back to the point about, developing our own kind of capability as a national sovereign capability. I read somewhere that, to be regarded as an advanced nation, you should either have, well, if you're a very, very advanced nation, you'll have 3 types of high-tech industries: the aerospace industry, so, making planes, etc., electronics industry, and a nuclear industry. And, I know that Australia does, manufacture some parts for Boeing, for instance, so we have some capability there. We've got some, maybe not exactly electronics industry, but I think our software and development industry is very strong. And then, the Australian government, successive Australian governments have invested in maintaining at least a certain level of nuclear science technology capability, and that's in the form of, having our National Nuclear Laboratory, ANSTO, right? And so, ANSTO is really a great example on how to do nuclear right, because we operate the Opal Research Reactor, which does a combination of things. It makes medical isotopes, as you know. 1 in 2 Australians will have a medical procedure with nuclear medicine. And we also make things called, what they call these silicon ingots, where we fire neutrons into a big solid piece of silicon, and it changes some of that silicon into phosphorus to make high quality semiconductors, right? That's another line of business ANSTO does. And the third thing is that these neutrons, these subatomic particles that don't have a charge, when you send them through a material, they will scatter and create a pattern in which you can work out what the atomic structure is like. And so it's basically like a material science research tool. And to do all that, you have a very reliable reactor, and we have a very reliable reactor that operates 300 days a year out of 365, which is really, really high. It's almost like it's on par with a power reactor, because on average, the uptime for a power reactor is about 80%, which is really high as well internationally. So I think that, we've got that national capability at a base level, and that gives our country options. So I think we're in good stead to expand, nuclear science technology research, for sure.
So just going back to the real basics of the nuclear industry, your starting point is at the moment, you basically have to mine uranium, and Australia is pretty well blessed with uranium reserves. We've been mining uranium since the 60s commercially and exporting it, I think, out of South Australia. And we bring it, my understanding is we bring it up at least to yellowcake before we export it, so we do some processing. But how hard is it to go from that sort of level to at least enriching and producing nuclear power rods and things like that? Yeah. Is it such a gigantic step, or what's the sort of?
Yeah, definitely, it's a special piece of tech. So what you're referring to, is something that the industry called the fuel cycle, the nuclear fuel cycle. So you go from, mining the uranium out of the ground, which, for example, in Australia, you must have heard about Olympic Dam, which is a copper mine, and they take out the uranium as a kind of like a side kind of tailing, and take the uranium out. So it's very rich. And then from there, you would chemically process it, get the yellow cake, which is chemical formula U308, and then you would if you want to make fuel rods out of it, you would do a little bit of light enrichment. So a little bit of background, like basically when you take uranium out of the ground, there's different types of uranium, you can call it that. Uranium-235, which is the fuel, the actual fuel for a normal pressurized water reactor. And then you've got what they call the natural, the uranium-238, which is the isotope or the type of uranium that is more prevalent, but doesn't actually undergo nuclear fission. So sorry about all that science. I mean, it sounds a little bit like the Big Bang Theory and all that, but basically you have to increase the percentage content of that uranium-235 from about 0.7% to about 4% to get reactor fuel, so to speak. And to do that, currently, internationally, the way to do it in most places is to put them into centrifuges so that the slight mass difference between 235 and 238 will allow them to separate out, and then you will collect up more of that uranium-235 for your reactor fuel. And the audience might be interested to know that ANSTO actually had a uranium enrichment program back in the 70s and 80s, but that was all shut down for whatever reason. And and nowadays it's more difficult to get into the uranium enrichment game, just because the established processing facilities are just so well honed in and economic. It's hard to kind of get in on that piece of the pie, so to speak. So then you have your reactor fuel, those fuel rods, which are manufactured, those little uranium dioxide pellets. They go into these really, really long fuel pins, which are about 4 meters long, 4.2 meters long. And these
what are they made of?
So they're made of zirconium, or an alloy of zirconium called zircaloy. And the reason why you have that is because they're transparent to neutrons. Because when you've got uranium splitting, you've got 2 to 3 neutrons coming out, and then they get absorbed by other uranium atoms and they split and release energy. But the thing is, you don't want those neutrons to be absorbed by anything, right? And so it goes through something like zircaloy, which is kind of like transparent to neutrons. And then, that's how your reactor systems work, is to actually make sure it conserves those subatomic particles, neutrons, as best as possible. So those fuel bundles is basically the core of what drives most of those power reactors around the world, these pressurized water reactors, of which there are about, currently today is about 300 odd pressurized water reactors out of 439 reactors of all different types.
But I think it's really important that the Australian government, and it doesn't matter which party's in government, is to get Australia to add value to everything. And it sort of astounds me that since the 1960s we've pumped out the highest grade iron ore in the world and shipped it away, yet we haven't moved to the next stage to actually make the steel here and then on-sell that. So we're very poor at value adding, and so I think probably one of the things they probably should focus on is at least value add to the uranium.
Yeah, I forgot to say that Australia supplies about 10% of the world's uranium. So in fact, what's interesting is that we export so much uranium that it's enough to basically power the whole of the, national electricity market. The amount of
and that's content, only limited, right? But that's only digging up limited reserves. The number of reserves that are actually locked in the ground by different states.
Yeah, that as well. Because we've got like 33% of the world's economically recoverable uranium right? But we're still only exporting 10%. So it means that places like Kazakhstan are really kind of have really ramped up their uranium production.
If we just move on now to nuclear power itself, as you said, there's over 400 reactors worldwide, and they vary from a lot of different countries. I mean, even Argentina has got a couple of nuclear reactors, I think. Brazil. So, and of course, the countries that were behind the Iron Curtain have got reactors as well. You know, places like Bulgaria and that. And so there's a number of countries in regards to, you would think, well, Australia is, you know, sort of this big and this is an advanced economy and that. You think, well, there's no reason why we shouldn't be sophisticated enough to have a nuclear reactor if the Bulgarians have got it and all these other people have got it. So, do you think that's one way to sort of approach the situation with the public in regards to the general apprehension, I suppose, to say, well, other people are doing it. We've got the one of the most important things about Australia is it's geologically very stable. All its land mass is fairly stable, so we don't have some of the problems that Japan experiences and other countries around the Pacific Rim. So we've got a great environment to have them. Probably in a little bit of issue with water in some locations because nuclear reactors need a lot of water supply. True.
Just for cooling, that doesn't really burn off the water. Just to cool.
You need the cooling.
Like water a little bit,
But, so you need a reasonable supply of water at the site. But overall, we're fairly well positioned as a stable political country, stable geology. There's no real natural reasons why we're not a candidate for having them.
Yeah, like, I mean, what you stated is absolutely completely repeated by a visiting IAEA delegate. So we had, I think, Deputy Director General for Nuclear Power from the IAEA actually come and visit ANSTO, and you know, this Chudakov, his name is Mikhail Chudakov, and he asks why we don't have nuclear power. He's asking exactly the same question you're asking, because when he comes to visit ANSTO, he just sees, okay, a good mix of different ages in our workforce, a reactor that is operating reliably and safely and cleanly. You've got a wide breadth of capabilities here. You've got a nation that does project management right. You know, we're a great importer of technologies, great importer of ideas and skills and making it work, because, you know, we're a very flexible and resourceful kind of country. But I think the question as to why we don't have nuclear power right at this moment, you know, I think I have to give a little bit of background, is that you can kind of think of Australia as a very, very well-blessed country, blessed with all sorts of options, right? We've got gas, we've got lots of land, we've got lots of, like, we've got some wind resources, we've got lots of sun, we've got tidal waves, we've got coal, we've got everything, even uranium. So in the past, it's always been about how do we create an energy system that is least cost and reliable? And in the past, it has been coal, definitely. Because even today, the NEM, the National Electricity Market, that combines the 5 states on the eastern seaboard, is 65% powered by coal, right? That's just a fact. And it's hard to move away from that, especially when you've got a system, a thermal system, that can be dispatched at will, that's not intermittent, that's reliable, right? But it's just that because a lot of increasing kind of market share of renewables, it's actually taking the market share away from coal, and they're making it hard to maintain a profitability, and that's why they've been shutting down, right? So in the future, if we have lots of, say, renewables and we have to back it up with gas, but then people might start asking the question, you know, can't we have maybe a base load power supply that's also non-CO2 generating? And, you know, nuclear power is being used in that function overseas. And that's, I think, going to be the key, to communicate to people.
I suppose it's only the CO2 issue that's brought it up to the forefront, because up until 2007 with the Rudd government and then going to Copenhagen and all those sort of things, Australia was delivering very cheap power through its national grid and coal power. So for the nuclear power industry to get a leg up would have been almost impossible, because you're delivering to the people's door somewhere between 10 and 12 cents a kilowatt, and delivering to industry for somewhere between 4 and 6 cents a kilowatt. I mean, I know, I know when I was in the Air Force, the cost coming onto the base of electricity was actually below 4 cents, and that was, you know, up to the 90s.
Yeah, for sure.
So that's always going to be a problem in regards to the pricing increase of electricity since 2007, and anyone can look at it in a graph. And basically, all that rise has been politically influenced, not the cost of coal going up, not the cost of generating up. It's simply been subsidies, grants, and all the rest to renewables and that. So it's thrown the market out, and it's now sort of distorted.
You know, it's a question the government, both federal and states, contending with, right? Because you know, for example, I work with a Professor Stephen Wilson over at University of Queensland that looks at the energy market and tries to understand, you know, why the wholesale electricity price has been going up and up and up in the last decade. And, you know, from what he sees is that, in fact, he's got some brilliant graphs, and, you know, maybe he could be a guest for your show in the future, he actually plotted, like, every kind of day over an entire year, the fluctuation of the wholesale market price for electricity back, say, you know, 10 years ago, thereabouts, in Adelaide, and now. And nowadays, the price fluctuation is just everywhere, because, you know, some days you might have a lot of wind, other days you might have a wind. And then, you know, and that kind of volatility really, really spikes the market price. And overall, that's what kind of lifts the overall kind of price of electricity. So then in the future, then you might say, okay, if we go towards, say, a renewables plus gas future, but gas, of course, is going to be in much higher demand because everyone will be trying to transition to a low CO2 future. So then, you know, Australia as a country has to ask the question, well, should we export all that gas and make a lot of money, or should we, like, keep a bit of it and supply our own electricity supply? Or maybe we could consider having nuclear power to supply a little bit of that backbone, base load, low CO2 generation. So, yeah.
Okay. Yeah, I think that's one of the big problems as we go ahead is getting a return on your money, regardless of without subsidies and without guaranteed feed-in tariffs, and, you know, just on a level playing field for everyone. I suppose that's what we need to be fair to nuclear to get a leg in. But with the focus now on net zero 2050 and all that, it has to come into the mix. But so that leads us on to the next part of the conversation.
So I think I really like the point that you just gave up. Sorry, I just interrupted.
Yep.
But the idea of the subsidies, right? It's actually, you got to kind of think of it the other way, I think, because, like, having conversations with other people. Because if you think about it, like, when Australia heavily invested in, say, even baseload coal generation, it was basically a national market. Basically, it was owned by the government, and they kind of bankrolled the whole operation, centrally planned, right? And carefully planned as well, because you had those coal-fired power stations pretty close to the load centers in cities and in industry. But you can kind of think of their builds as being kind of like a subsidy because it's bankrolled by the public. And then also with the renewables, about 10 years ago, there were lots of incentives to see the entry of wind and solar on the market, and that was to encourage their uptake. And then eventually those kind of subsidies dropped off. But these are kind of like little incentive schemes to just increase the possibility that they'll be taken up on the grid. But I also think that, you know, even with nuclear, to encourage nuclear on the grid, possibly in the future, would also require lots of government support as well, just to make sure it's done right, right? And then it's only from that learning of the first of a kind plan do you really can be assured that you know exactly what you're doing, and then you can really roll them out at low cost. So, you know, it's not exactly, yeah, it's just the point that kind of Professor Stephen Wilson made that I thought was very interesting.
But I'll also point out there, Australia's a young nation, never had any old money. It's like when the ABC came into force, the government had to bring that. It wasn't going to be commercial because there wasn't a lot of old money. If you go to Europe and the United States, you had the people who made zillions of dollars in the railroads, oil, or people like the Rothschilds in Europe made money over hundreds and hundreds of years of trading. You know, people going back trading with the East India Company and things. There was a lot of old money to get these things started. I mean, in the UK, there were a lot of private railroads, or was mostly private railroads, because it was simply that money was available from those people. In Australia, we never had the luxury of having old money, people with, you know, no Gettys. We didn't have any Rothschilds or anything like that. So we didn't have that capital market to get these things off. And so it was done by the governments, all our railway, all our electricity, all our water and that. Otherwise, there just weren't any people with that sort of capital.
Yeah, I think,
so that's one way to look at why those things sort of started.
Yeah, but, I think sorry, go on.
Yeah, but if we just move on to nuclear power, if we got the tick in the box today to say, right, we want, the government goes out, we've got to give a license to someone, or we've got to actually build it ourselves. If the tick was put there today, what would people be looking at on the commercial market? What could they actually buy or get built as a reactor today?
Okay, so like broadly speaking, there's two main types of nuclear power reactors. The really, really large ones, which are the traditional types of nuclear reactors. They output maybe 1,000 megawatts, right? I mean, the largest coal-fired power plant, I think, in Australia is about 750 megawatts, right? So those are really, really big units. And the other thing as well is that, you know, in the West, say, you know, in the US or France or the Great Britain, the massive build out of these really large reactors happened like 30 years ago, right? And so the supply chain has been weakened. And currently, you know, the US is building two of the AP1000, you know, 1,000 megawatt
in Georgia.
Yeah, in Georgia. And the French are building a unit of EPR over in Flamanville, and they're building like 2 units over in Hinkley Point C. But the long story short is that these are kind of like, you know, multi-billion-dollar kind of investments, things which possibly, you know, companies in Australia won't have the balance sheet for to actually swallow as an entire project. So the alternative is that, you know, the US has innovated and said, okay, we can see the difficulty of building large reactors. What we're going to do is we're going to miniaturize that technology, like take all the learnings in the last 30 years and make a smaller reactor so that can be made in a factory, so that you can reduce the cost, you know, per pound for pound in terms of power, but then also up the amount of quality and up well, reduce the time it takes to construct them as well. And these reactors, we're talking about, say, you know, anything below 300 megawatts is regarded as a small modular reactor. And it gives like superior safety as well, because you could have them all positioned in a common kind of swimming pool to cool them down in case, you know, you have a major kind of catastrophe like Fukushima or something, where it takes out all your diesel generators or have a massive earthquake. It doesn't matter, because all your cooling potential is in the pool to cool those reactors down after they shut down. You know, got to keep in mind they're still giving off a bit of heat, and that needs removing. So I think for Australia, you know, the correct fit for reactors is pretty much, we're looking at small modular reactor types as being the type of reactors to consider. And currently there are 2, I would say, major contenders for the small modular reactor design. One is NuScale, and one is BWRX. That's the General Electric design. So they're
if
all
we
kind
just,
of going under license,
yeah.
I think.
If we could just kill off the idea of ever having a big reactor in Australia, I'd just like to touch on those two generators, two reactors being built in the United States. I think they got the tick in the box of 2009. They're supposed to be online by 2016. They're supposed to be built for $9 billion. It's now 2022. Neither reactor's online yet. That's the time overrun, and we're now up to nearly $28 billion. So knowing that how well Australia's delivers projects, I could see if we built the equivalent of those two reactors, we'd probably be paying $50 billion in about 50 years delivery time. So
yeah, look, I mean, I don't hear much about anyone thinking about building large gigawatt reactors in Australia, put it that way. I mean, what's interesting though, people might be interested to know, was that at one point in time, Australia did consider building like 10, 15 units of AP1000. And, you know, we never went forward with that, probably for good reason. But yeah, but currently, if we were to consider having nuclear power, it would probably be of a small modular reactor for IT time. And when I say that, you know, it's not like you just build one itty bitty kind of unit. You can, for example, with the new scale design, they output 77 megawatts each, and you would just deploy like 12 or 6 at a time to give you a sizable amount of generation.
I think on Sunday night, and it's been shown a couple of times on the SBS, how to build a nuclear power plant, and they did the whole show revolved around the old style, you know, pumping 9,000 cubic meters of concrete, and then of course all the reinforcement just to put your base down, and actually you had to put that base onto bedrock. You couldn't just put it on shale or something like that. You had to make sure you got down to a point where there was bedrock and put that base, and that was just the start of it. So it was an interesting part of the show, just that exercise of pumping in 9,000 cubic meters of concrete and all the steel that it's sort of incredible. So I've got a couple of pictures there from the Georgia site. You might want to comment on some of the photos, so I'll just do a screen share.
Sure.
This is the Georgia Power. I presume this is their cooling system or something on the river. And one of the big delays that happened was after Fukushima, because of the problems with cooling, they actually had to do a modification to make sure they had extra cooling capacity to make sure something like a Fukushima didn't happen. So there was
so this massive kind of rectangular looking thing above the containment structure. Yep. So inside this containment structure is actually a reactor, which is a lot smaller. But this kind of square looking thing, which is the cylinder, is actually a huge water reservoir that they use to, you know, basically use natural convection to passively cool the core after it's shut down. So that, you know, if you had something like a Fukushima event and you have station blackout, so say the tsunami comes in and takes out all your power grids, so you can't actually draw power in. Because a little bit of background for the audience, like once you shut the reactor down, the kind of fission fragments, the decay, the fission products, is still emitting a bit of heat. So as a general rule, it's about 1% of the operating power 1 hour after it's been shut down. So you say 1% doesn't sound very big, but if you've got a reactor outputting, say, you know, 3,000 megawatts in terms of heat during operation, 1% of that is 30 megawatts, right? That's like 30,000, you know, like how many ever light bulbs there are. There's a lot of heat still to get rid of. And usually what you do is you just take power off the grid and you run some pumps to just keep the core cool, right? But in the case of Fukushima, what had happened was that they built the reactor power plant too low and also the seawall was too low. And so even they safely shut the reactor down and they had the diesel generations kick in, when the tsunami wave came, it was 15 meters, and the seawall was not high enough to protect against that. They had the diesel generators in the sub-basement, it flooded it, and that's what killed those diesel generators that was keeping the pump running. And in fact, there was another nuclear power plant even closer to the epicenter of the earthquake, which survived just fine because they built it higher and they had a high seawall. So it just comes down to things like that, right? So with the new reactors, it's always about, you know, enhancing safety, and that's why with the AP1000, they've got that water reservoir on top, so they don't have to rely on, you know, diesel generation or diesel backup power. Yeah.
Were you surprised that after Fukushima, places like Japan just basically packed the bags up on nuclear power, and same with Germany?
Well, you might say that, but actually they're not. They've gone back to nuclear power. Obviously, the regulator, you know, tightened everything up, and they had a safety review on all the nuclear power plants, because at the high point, I think they've still got about 40 odd, you know, nuclear power plants, of which only 9 have been given a license to go back to operation. Because you see, at the end of the day, you know, Japan is an island nation and they don't have a lot of, you know, coal resources and whatnot. And so they've just been like importing gas like crazy, you know, just to make sure that they can supply their industry with power. And now, you know, now after they've reviewed the safety plan and the systems of all these reactors, you know, 9 of them are allowed to go back up to power, and they're still thinking about building more reactors. And I think what's really important to stress as well is that, you know, it's not often well known in Australia, just the sheer amount of build out that we're going to be looking at in the future for nuclear power in our backyard. So for instance, you know, in India, they're already building more reactors. They've got like a heavy water reactor design that's their own, that they're going to build out as well. With China, they've expanded their nuclear power fleet, doubling it within 5 years from 27 gigawatts to about 54 gigawatts. And they want to target about 130 gigawatts by 2030. So, you know, that's only, what, 8 years' time, right? And to give you some context, the current country with the most nuclear power at the moment is the US, with about 99 units of, you know, power reactors. So we're talking about by 2030, you know, China will have more nuclear power capacity than the US. And it could possibly be that there's been studies to show that they want to have, say, 28% of their country powered by nuclear power by 2050, which will bring the capacity up to 500 gigawatts. So more than the entire nuclear power that's currently existing in the world today. You know, that's the central plan to do low carbon, you know, cohesive energy generation.
But it sort of beggars belief, like in Europe, with Germany in particular, sort of deciding to close nuclear power plants and going the renewables way, and at the same time completely dependent on Russian gas to keep things going. It seems counterproductive in regards to your sovereignty, in regards to cutting things that actually keep you independent and keep you strong. So
yeah, I would say so. I mean, it's very confusing to me why Germany decided to shut down 3 of the 6 nuclear power plants last year, for instance, and they're planning to shut the rest of the 3 off. I'm not sure if they're going to think about it again because, you know, of what's happening in Ukraine at the moment, but it doesn't seem very prudent.
Just in regards to the older generation nuclear power stations, the sort of I think they're 1.1 gigawatts basic unit sort of thing. The United States, especially with the last 2 in Georgia, obviously showed a lot of problems in regards to their retention of expertise. Is expertise in building nuclear power sort of been transferred well to other countries, and say like South Korea, if you wanted someone to build you a nuclear power station and put out a tender, would it be more likely that someone from South Korea or even Japan with those current skills have got a good chance of getting it, rather than somewhere like in the United States, where it seems to have lost a lot of their expertise over the last 50 years, because the real big drop off in number of plants being built by US manufacturers.
Yeah, that's a really good point, and I think that a lot of people have made the comparison between, say, naval ship build-outs and nuclear power build-outs, because what you really want to do if you want to have a kind of long-term cohesive build-out program is to make sure that your workforce is on a rolling kind of schedule, where you're just like building out one unit and then you're moving on to the next unit and next unit and next unit. And the points that you raised about South Korea and their ability to not just build at home but also at the UAE, like 4 units of the APR 1400 is a big success story because it was on time, on budget. So I think somewhat of the myth that you can't build large reactors is simply only a myth. It really depends on whether a country decides upon actually resourcing it correctly, right?
And also the green tape and red tape thrown out during the exercise. Yeah. Because from what I understand, with especially the ones in Georgia, there was constant matters going to court and environments, and it just it was just continuous.
Yeah,
so that's a problem. Whereas I presume in countries like Korea, where you're accepting of nuclear power, you don't have those same barriers. And then in the Middle East countries, they just want it, so they're not going to. Well, there's not a lot of green environment they have to worry about anyway. But they don't have the same public barriers as you find in European countries, United States, and in Australia.
I think you can still do nuclear right in the West. It's not simply about people have homes, they have communities. You can't just like steamroll in and say, okay, you're going to get a nuclear power plant, right? But I do think, though, that there are a lot of regional centers which are traditionally very kind of blue-collar, industrial-based, and they understand, the connection between having a good, stable, solid piece of power generation and the way that feeds into an industry. And in those areas which, say, have a coal-fired power plant, which might be under threat of closure, those could be communities that are very welcoming of a replacement thermal plant, but one that doesn't pollute in the way that a coal-fired power plant pollutes, for instance. So I don't think that it's necessarily extremely difficult to convince people to have nuclear power. It's just that you have to respect people's kind of feelings and ideas and thinking, and you have to do those stakeholder engagement exercises early. So that people are get familiar with that technology and kind of like let them decide on whether they want that technology in their community.
Well, I was having a conversation with Mike Young yesterday actually, and he previously worked for Vimy Energy and Mining, and was involved in the uranium industry. And in that conversation, he indicated that locations of nuclear power plants would be a perfect fit for old coalfield places, or where coal-fired stations and mining was, because the infrastructure's there in regards to the resources, the actual workforce, and a fairly skilled workforce. So of course, it's a new industry, you have to train them, but they're capable, and just the general infrastructure, and also you already got the connectivity to the grid.
Yeah, absolutely. So, that's all very true.
Yeah, so that's why this is a subject. Well, this is regional RAP we're talking about, and a lot of people might not sort of relate nuclear energy to the regions. But the thing is, the only place that's going to have a nuclear power plant is going to be out in the regions. So we're likely to be the beneficiaries from the introduction of nuclear power and that. Because I don't think you're going to build one somewhere around Bondi or Potts Point or...
The property is way too expensive over there. Like, you'll go broke just buying up the property, right?
Yeah.
But no, it's really
so
interesting what you brace, yeah, because like, I mean, the idea of like, you know, how to where to build, the idea of like what they call like brownfield swap outs is something that's common like internationally. It's not just something thought about in Australia. They've thought about these kind of thing, like for example in Canada, right, where they've already got an established nuclear power industry, but they do want to swap out some of the coal-fired power stations in the west of Canada, right? So yeah, I think it's actually quite smart because, as you said, you know, all the grid infrastructure is there. You don't have to build massive grid infrastructure out in the middle of nowhere to connect up, say, you know, renewable energy zones, and also, you know, you can always put nuclear power plants relatively close to the load centers, like, you know, population centers and whatnot, because obviously there are transmission losses, you know, if you have a very, very large grid. And also, you know, a lot of people don't know that, you know, nuclear power plants, they are nearly on all the time. Like in the US, on average, throughout the whole year, they're on like 92.5% of the time, which is like, compared to a coal-fired power station, it's about 50%. For wind, it's about 33%, and for solar, it's about 25%. So if you build, it might sound expensive, but the amount of power it pushes out, and the fact that it lasts for 60 years instead of 20 years, and, you know, just the amount of care and the maintenance that you put on a reactor, it's very, very different from some of the other energy options.
I suppose just before we've gone nearly an hour, but one point we'd like to touch on is with with our new renewables that have come in now, we had sort of, you just mentioned there, the sort of life of type, you know, 20 years if you're lucky. Then if they're supported by batteries will never go to last 20 years. So you have a disposal problem in the future that doesn't seem to have been well addressed at the moment. We still have in the United States wind farms dismantled and the blades are still there, and they're actually thinking of burying them. So in regards to a nuclear power station, what are we looking at for decommissioning at the end of the day? If we pull down a coal-fired power plant, most of the superstructure, we probably could send it off to the scrapyard and sort of melt it down to new steel and stuff like that, plus salvage all the copper. There'd be obviously a bit of trailings and dirt and stuff that all have to be cleaned up, and concrete base and all that sort of have to be thing. In regards to a nuclear power station, how many do you know that have sort of been decommissioned, and sort of what was sort of left there in after the event sort of thing?
Okay, so like, I mean, so there's actually three things I want to talk about quickly. So obviously everyone's interested in nuclear waste, like how much nuclear waste is generated by a nuclear power plant, and also at the end of life of a nuclear power plant, what do you do? And then also maybe in Australia, have we actually decommissioned our own nuclear reactor? Actually, yes, you know, Australia has decommissioned its own nuclear reactor. It was only a little small reactor called Mawata, which is, I think, an Aboriginal word for like fire starting, or because it was a very small reactor. And I actually worked on the decommissioning project as well, because what you do with a nuclear reactor is that some of the bits and pieces does get like activated by the radiation. And so what you usually do is you just wait for the radiation to die down to an acceptable level before you go in with jackhammers, of course, completely enclosed in a negative pressure containment, and then you can basically demolish it and return it to a greenfield site and have a place where you can bundle up, you know, the demolished bits and pieces and put it in a repository, possibly underground. Because you have to understand, it's like only lightly radioactive after it's been decaying for a long time. With regards to nuclear fuel rods, they do come out of fuel like warm, as I said. Those fuel bundles, they stay underwater for about 5 to 10 years in what they call a spent fuel pool. And then after that, they become cool enough that you can actually put them in a flask or a concrete flask, where they're just sitting out in a parking lot doing, basically not hurting anyone, emitting a little bit of heat under surveillance control of that nuclear power plant. And then, you know, you've basically got the option of either recycling that fuel to be burnt in an advanced reactor, or you can just put them underground, maybe like underneath about 800 meters in a rock formation that's appropriate. So, and it's not just a dream, you know, for example, you know, in Finland, they are opening up like a first of a kind, a deep repository to put the fuel away, because the government just asked these people, like, what do you want to do? We have to have a solution for this. And they just slowly kind of work towards that, delivering on that. And so the first geological repository is just opened up, right? It's not something that is unsolvable, especially when you ask a nuclear engineer, what do you do with the waste? You know, for a nuclear engineer, the engineering of a reactor is a lot more complicated than waste, because waste is just sitting there. And what most people don't understand is that nuclear waste destroys itself because it's decaying away. So the most radioactive portion of the waste, like the strontium and the cesium, half of it disappears within 30 years. So if you do the maths, 10 times 30 years, you would have less than 0.1% of the original content left of the strontium and cesium. Of course, you still have the uranium, a bit of plutonium and that, but they are only very lightly radioactive. Okay, so it's not this terrible thing that will forever, you know, threaten humanity. It's actually something that is quite inert eventually, that destroys itself.
I think it was interesting. I mean, we've seen Chernobyl, but we've also seen over the years and that different pictures of the landscape around Chernobyl and the wildlife and that's there. So there's no two-headed birds and there's no two-headed snakes or lizards or anything. And they've got a lot of these wild ponies in the area as well.
Yeah,
and that herd of ponies seems to be going okay. Its numbers increase, so it hasn't had a fertility problem, and it doesn't seem to have a lot of mutations or anything. They seem to be fairly healthy. So
yeah, and
that must be sort of encouraging in regards to, even though you can have a catastrophic disaster, really the landscape can bounce back in a reasonable sort of time. I mean, not that probably we want to run around in there, but the horses seem to be doing fairly well.
That's true. And you know, even like, for example, in Fukushima, for instance, you know, I have a colleague that went over there, and he brought along like a dosimeter, you know, a device that measures the amount of radiation uptake. And the highest dose that he got was when he got into the plane, and the plane went up, you know, at 40,000 feet. And at that level, you have less atmospheric shielding from all the cosmic rays and the solar, you know, the dose from the solar flares and whatnot. And he actually couldn't find, you know, of course he didn't go into the Fukushima reactor itself, but in the surrounds, you know, there wasn't that concentration of radioactivity that he was looking for. So in some ways, you know, from a nuclear engineering perspective, the containment of the, you know, Fukushima power plant units 1 to 3 did their job to an extent, right, to prevent the large release of radioactivity that Chernobyl had. And I think, you know, as nuclear engineers, we do take those lessons seriously in order to engineer a safer reactor in the future.
Well, we've gone over the hour, and we do have another interview with you in a few weeks' time, talking about what we can expect from the nuclear industry in the near future and the distant future, and what advantages are there for Australia to seize. And that, I think probably that's the word we need. We need to seize these opportunities rather than let them pass us by. And I hope the people like yourself and your colleagues can encourage the government to seize the coming opportunities in the future. So I'm looking forward to that in a few weeks' time. So thank you very much for coming on. I hope you enjoyed the experience. If you could just stay with us for a sec, I'll just do a premo for next week and have a quick conversation.
Yeah, definitely.
Thanks very much.
Thanks for having me. It was fun.
Well, if you have enjoyed tonight's show, please like, subscribe, and follow us on Facebook, and subscribe to the YouTube channel. Next week, after a lot of twisting of arms and wringing of hands, it looks like we've finally got someone from the Climate Council to come on and talk about IPCC AR6, which was released probably September last year. I think the working paper for Work Group 2 will be released next week. So we're hoping that they'll come to the party. And in a few weeks' time after that, we'll have someone speaking in regards to COP26 that was in Glasgow. So join us again next week, and thanks very much for watching.